Hello and welcome to my video series on the Modular Breeding Program Simulator. In this video I want to present the different trait types you can simulate in MoBs. When it comes to different trait types, we first off have some predefined trait architectures ranging from additive traits to dominant traits to quantitative epistatic traits and qualitative epistatic traits. In the R package, those are available via those parameters. In the web interface, you have here the phenotype information module where you would enter how many QTLs of the different types you want to have. In addition to that, you have a variety of other parameters like the trait heritability, repeatability, if those traits are of maternal or paternal origin, or if you want to apply some transformation to have not to model like binary traits and those kind of things. In terms of the predefined architectures, the first one are purely additive effects. In this case, we are putting an effect on a single marker and are simulating a single effect drawn from a random normal distribution with mean 0 and variance 1. And as such, the effect of 0 and 2 are polar opposites, and a heterozygous individual in the marker will have no change to that trait. Next up, we have dominant effects. In this case, the heterozygous individuals and those homozygous in the second allele have the same effect, whereas genotype 0 will have no difference to the trait value. Next up, we have quantitative epistatic traits. Those are caused by interactions between two markers and are designed in a way that we are first drawing 3 values from a random normal distribution for both markers, then sorting those values according to their absolute value, and after which multiplying the effects from the different markers. So if you would imagine the effect of the marker combination 1, 1, we would take the median value of the first draw and the second draw and multiply those. The idea behind is that the lowest trait value is put on the marker combination 0, 0, and whenever increasing one of the two directions, the genotype, the trait value will go up. So the highest value will be for marker combination 2, 2. Lastly, we have qualitative epistatic traits, and those are designed that we are for each of the 9 possible combinations having an independent effect drawn from a normal distribution again, with the key idea behind that in the two corners 0, 2 and 2, 1, 0, those effects we are here taking the absolute value, and for all the other values we are taking the negative absolute value to have like the positive effects in opposing corners. And those are our predefined architectures. Next up, I'm going to talk about correlated traits. The idea behind is that when we are modeling correlated traits, we are taking these originally defined traits and generating new traits as linear combinations of the old traits. The weights of these weighted traits are calculated via a Cholesky decomposition of our target correlation matrix. This first off sounds a bit complicated, but in reality is more simple than you would first think. So if we are imagining having a target correlation of two traits of 0.2, we would first calculate the Cholesky decomposition like here, and next up calculate the new effects for trait 1 as the first column of this Cholesky distribution, So we are basically only taking the old trait values, and for the second trait we would here take 0.2 of the old trait 1 effects and 0.9797 of the old QTL effects of trait 2. We are also doing a standardization to have like equal weighting between the traits, but that's more of a technicality. What's to note here is that the number of QTLs thereby will change for each trait, but as you can already see here, most weight will still be put on the old traits of that QTL. The main advantage of why we decided to do that is that for quantitative traits, usually the exact number of QTLs is not as important, but via doing this, we are ensuring that we have correlations that are consistent over time, so independent of LD structure and those kind of things. Lastly, if those effect architectures we've defined are not enough for you, you also have the possibility to define trait architectures yourself. For that, I'm switching here to R and will show you how to do that. First up, you would generate as usual your population via the creating diploid function. So let's say we are generating a population with 1000 markers and 50 individuals. We would now generate a trait and store this in an object with, as I'm here wanting to generate an additive trait, I will name it like real BVs of additive structure. I'm defining a matrix, and in this matrix each row is corresponding to one QTL, with the first value coding which marker I want to put this effect on. So for example, marker 42. The next value is indicating what chromosome I want to put this on, so chromosome 1. So this effect will be on markers 42 on chromosome 1. And next up, I'm entering 3 values for the effect of the genotypes 0, 1, and 2. So for example, 0, 0.5, and 1 to have a purely additive effect. Let's generate a second trait. So marker 234, also on chromosome 1 with, for example, effects minus 0.2, 1, and 0.5. So basically randomly chosen. Those are 2 effects, so we want to put them in 2 rows, and we want to fill the matrix by row to ensure the matrix to look like we want it to look like. So like this. To enter these as our trait, we are now using the function creating trait, and here entering the population that needs to get the trait and putting our trait matrix input as the parameter real BVE additive. So, and after this, our trait is generated. Let's quickly check. Our population now looks like this. We have one model trait that has underlying QTL. We didn't modify the trait name and are already set. To evaluate our traits initially, we have to run our breeding diploid function on the population, and afterwards can extract breeding values and so on. So for example, via getBV, we could look at our population and extract our genomic values for generation 1, so our only population. So this is basically all that's done. We here have values for the 50 individuals. We could extract the genotypes to verify, but I will skip on this right here. Similarly, you can also generate traits for multiple markers, so epistemic effects. In this case, it would look rather similar. With the key addition that we now have to specify 2 markers. So for example, marker 10 and and marker 100, both on chromosome 1. And now we have to provide 9 values that are coding effects of marker combination 0, 0, 0, 1, 0, 2, 1, 0, and so on. So let's just put 1, 2, 3, 4, 5, 6, 7, 8, 9. And this is just one row. So this would be a very simple trait that's just putting a single effect on this marker combination of the genotype 22. Oh, it's actually one too much. And via using the create trait command, we can now enter this as the real BV mult and are again all set. This can either be entered as a new trait to the existing one, or via entering replace traits we can remove all traits that were existing beforehand. In case you're working with multiple traits, you can provide each of those traits, each of those marker effects separately via a list. So, for example, to have 2 traits, we would generate a list. And the first list element would be the marker effects for our first trait. The first list element are the marker. These are the marker effects of first trait, and for the second trait, it doesn't really matter of what to enter here. But now our really BV additive object is a list containing QTL effects for trait 1, QTL effects for trait 2, and basically same command and same code as before. Let's run those lines. We now have, I didn't replace traits, so maybe also do that. We now have 2 traits which both have underlying QTL. We now evaluate those traits and now get breeding values for both traits. And this is basically all I had to present here. There is more information on traits in our guidelines that goes more in the technical details of like how heritabilities, repeatabilities, or traits with no underlying QTL are modeled, but that's rather straightforward and nothing really to show there. And with this, I'm already done with my presentation here. I'm thanking you for your attention and see you in the next one.